Okay, good afternoon, class. Let's get started. I just, like within the last minute, finished doing a curve on the grades for exam 3. So everyone's grade should have gone up by 6 points. The logic that I have behind that is this. Let me show you what I was thinking. This might be a little confusing to look at because I haven't made this presentable. So let me just make this bigger for you. So what you see here are the exam 1 grades, exam 2 grades, exam 3 grades, and then exam 3 with 6 points added. So the exam 3 grades are here in yellow, and then this is with the curve here in kind of orange. And so what I did was basically increased the grades by 6 points so that the class average on that test was here in green was a 68.07. The reason I did that is because if you take exam 1 in green there, exam 2 in green, and then the third one in green with the curve, if you average those 3 exam scores, it comes out to a 75. So the way I'm looking at it is this. You know, we get letter grades, A, B, C, right? D and F. A C means average, right? That's, if you get a C in a course, that means you're average. B is above average and A is above average, right? Exceptional. And then D is below average and F is below average. So what I was trying to accomplish was that the average score on all of the tests was average. Me thinking that a 75 is average. It's a midway point on a C. So I curved 6 points. So that may or may not help some of you. It just depends. The final exam is coming up, right? So the deal on the final is that I will replace your lowest exam with your final exam grade. So you'll be able to perhaps replace one of your low exams. Could be exam 3, who knows? It'll just depend on you. So that's the plan. On this test, after the curve, we had 3 A's, 3 B's, 2 C's, 4 D's, I think 6 F's. So kind of a mix. You know, we did have good scores. We did have low scores. So any questions with what I'm presenting here to you? On the exam, on the last problem where you had to do increase, decrease, and then concavity, the second derivative, the concavity, I did not grade that. I did not deduct points from your score if you didn't do that correctly. If you did it correctly, I added points, like it was a bonus. But I did expect that you got the first derivative part of that question right. So I know some of you went ahead and took the time to kind of redo a couple of the problems and submitted that to me. That's great. I haven't looked at those yet. I've been trying to get a lot of different administrative stuff done for all my classes, so I will take a look at that. So I guess what you have going for you right now, everyone, is that you have a final exam that will replace your lowest exam, and that final exam is going to have an automatic 5-point bonus because I hit my weight goal many weeks ago. So, all right. Any questions? Okay, all right. Well, if you want to talk about your grades specifically, I urge you to reach out to me so we can get, talk more one-to-one. But the final exam is going to be kind of high stakes for some of you. I mean, it's going to be a lot riding on that exam. But if you prepare and practice and put the time in, you can do okay. So, all right.
Sir,
so today,
it's everything, right? It's like from the beginning to what we're taking now for the final.
yeah, I think everything is fair game, fair to be on the final. But have I given you all the review? A review? No review yet. Okay, I will give you a review.
Okay.
I need to make the review more current. Usually the review is always based on the class. So like if the class did really well in the first few exams, then I don't need to really test that too much, but if there was like exam 1 and 3 were the struggle points for this class. Exam 1, the class average was a 75. And then of course, exam 3, the class average was a 62 before I curved it. So I would anticipate there will be information from exam 3 on the final, and in exam 1. But let me make the review and I'll get that sent out hopefully in the next day. Your final is on Thursday next week at 12:30. Right, so I think we talked about this before, but on the schedule, I know we meet at 1 normally, but for the final, we will meet on Thursday at 12:30 and we'll go till 3:15 for that test. We do not have class next Tuesday. So we only have 2 more class meetings before the final, today and Thursday. I know, don't get sad. All right, you ready? Any other questions? Let me check the chat. It looks like I have something in the chat here. Oh, is that homework 4.7? So I'm being asked about the homework for 4.7, antiderivatives, number 5 and 6. 5 and 6. All right, so for 4.7, number 5, we have f of x equals 3 square root of x minus 2 cube root of x. And we are asked to find the general antiderivative of this. So the only thing that we learned last time was that if we were trying to find the antiderivative of x to a power, we had this thing called the power rule, right? So if you have x to the n, the antiderivative of that would be 1 over n plus 1 times x to the n plus 1 plus some constant if the n was not equal to -1, right? Now, if n was -1, then it's the antiderivative of 1 over x, which we know is the natural log of x plus c. So we discussed that last class, right? So for this problem, we're trying to find the antiderivative. So the notation I used in class was that we were trying to find capital F, all right? That's what we're trying to find. Now, in order for me to do this, I need to rewrite this with x's to power. So I'm going to rewrite the square root of x as x to the half. And then I'm going to rewrite the cube root of x as x to the 1/3. that's just that's what those mean, right? That's what it means to take the square root or to take the cube root. It's raising it to those fractional powers. So now when I go to do the antiderivative, right, I'm going to use that rule. So capital F of X will be equal to, and let me just right now put plus C so I don't forget it. The 3 comes for the ride. We talked about that also, how when you're doing antiderivatives, if you have a constant in front of a function, it will come for the ride. Just like it did with derivatives, it does the same thing with antiderivatives. So we'll have a 3 here. And then here, our power here is a half. So I'm using this formula here where n is 1/2. And so I'm just going to plug it into the formula. 1 over 1/2 plus 1 x to the 1/2 plus 1. Now I'll figure out what that is in a minute. Okay, I'll figure out what all that is, but let me continue. Now -2, that -2 comes down. And then I'm going to do the same thing. 1 over 1/3 plus 1 x to the 1/3 plus 1. So just like when we were taking derivatives, every time we took a derivative, we had to subtract 1. And so we had to get used to like taking 1 away from fractions. With antiderivatives, you have to get used to adding 1 to fractions. So let's see, this becomes 3 times 1 over, let's see. If I do 1/2 plus 1, that's the same as 1/2 plus 2 over 2. So that's 3/2, or 3 over 2. And then that's exactly the same thing as the power. The power will be 3/2 as well. -2 times, then 1 over, now again, I've got to do this, 1/3 plus 1, that's 1/3 plus 3/3, that's 4/3. And then x to the 4/3, and then plus c. And the only thing really left for me to do is to take these 1 over things right here and flip them, and then multiply them together with the number in front. So when I flip that one, it becomes 3 times 2/3 x to the 3/2 minus 2 times 3/4 x to the 4/3 plus c. And now these 3's cancel, so I get 2 x to the 3/2. And then this 2 and 4 reduce out. So I get -3 over 2 x to the 4/3 plus c. And that would be an acceptable answer right there.
I have a question.
Yes.
I was under the notion that that plus c was per each term.
It could be plus c for each term, but then you would have 2 plus c's that you add together, which would still be plus some constant, right?
Okay.
Even if you said plus 2c, it's still a constant. You don't like it, it can vary. It can be any number. So
Okay.
yeah, you could combine them together and just call it c. That's fine.
So it wouldn't be wrong because if I got like 2x to the 3 over 2 plus c minus the second term plus c.
It wouldn't be wrong, but people would be like, why are you doing that? Just put 1 plus c at the end. It wouldn't be wrong, but it would just be like, yeah, you don't need to do that. I mean, saying that this is the answer plus some constant is the same as saying plus 2 constants or plus 3 constants. So let's just put 1.
That makes sense. Thank you.
Okay. All right. Now, on the next one on 6, f of t, so they're using a different variable, big deal. 3t to the 4th minus t cubed plus 6t squared over t to the 4th. So I told you again in class last time that when you have division like this, we do not have a rule yet in terms of how to handle division. The only thing we can handle is if we have x to a power by itself with pluses or minuses between them. This division sign is bad news for us, really bad news. But we get lucky here. We get lucky in the sense that we have a single term in the denominator. So I am free to rewrite this with each term in the numerator divided by the denominator. And that's just properties of fractions, right? I'm just like pulling this fraction apart. I have not found the antiderivative yet. I'm just rewriting the original function. These t to the fourths cancel, I just get 3 minus, now this one here, 3 of these go away. I'm left with 1 t on the bottom, so I get 1 over t here. And then plus I get 2 of those t's go away. I still have 2 on the bottom, so I get 6 over t squared here. That's where I am so far. I need to find the antiderivative. So I start thinking, okay, am I going to be able to handle this? I can look at them individually. The antiderivative of this should just be, so let's do this, capital F of t, okay? The antiderivative of a constant, should be the constant times the variable. Because when you take derivative of 3t, you would get 3. And then the next one is the special one. That's natural log of t, right? 1 over t, the antiderivative is natural log of t. You've got to remember that. Now, this last one is not natural log. This one you have to look at as 6t to the negative 2. So bring that t squared up and now use your power rule that we just talked about, which is to say plus the 6 comes for the ride, 1 over negative 2 plus 1, t to the negative 2 plus 1. I'm going to have a plus c out here. So do y'all see the difference between this 1 over t versus the 6 over t squared? One of them is the special rule. The other one is the good old power rule. I'm almost there. Okay, 1 over, let's see, negative 2 plus 1 is negative 1. So this just turns into 1 over negative 1, which is negative 1. Then t to the negative 1, then plus c. And just put those two together, make that a minus 6. You can leave it as t to the negative 1, that's fine. You could also just drop that t down below the 6, it's up to you. All right, I hope that addresses the questions. Yes. Okay. All right, good. Well, this was a good review because I know y'all were all getting ready for the test. So we want to talk more about antiderivatives today, right? And just what we want to do right now is take a look at some kind of odd problems, some weird problems that are going to kind of open up this new avenue for us to think about. It's kind of interesting. Let's just get through a few of the problems first. So let's do this example. Let's say I tell you that f double prime of x is equal to 4x, okay? I'm telling you that. The second derivative of some function is 4x. And I tell you that the first derivative of the function at 1 equals 8. And I tell you that the original function at 2 equals 4. I want us to find what the original function is. Okay, so think about it this way. I'm going to try and make you visualize this first. What we've been doing in this class up to this point, before we got to antiderivatives, is I gave you a function, right? Then what we could do is we could take the derivative of it and we would get f prime, right? And then we could take the derivative again, if we wanted to, and we would get the second derivative, right? That's something that we learned how to do, right? Give you a function, take the first and second derivatives. What I'm giving you here is this. I'm giving you the second derivative of a function. So I'm giving you this, right? And what I'm asking you to do at the end is tell me what what f of x is. So I want you to go back to this. I want you to somehow go from here back to here. But there's a problem. When I go from f double prime, if I try and go backwards, right, I do an antiderivative. But what is next to every antiderivative? What's at the end of every antiderivative? Plus c, right? which means that if I try and go backwards from f double prime back to f prime with an antiderivative, I can give you an answer, but it gives you a huge family of functions, right? It's an infinite number of functions. They all look kind of the same. They're just plus c moves the graphs up and down. So what we want to look at is thinking about the antiderivative of a function as a family of functions. So like if I give you a function 2x, the general antiderivative, can you all see this? If I give you if I give you that little f of x is 2x, the antiderivative is x squared plus c, right? X squared plus c are all these parabolas, right? It's all of these parabolas. It's the same parabola, just moved up and down. And there's actually infinitely many of them, okay? But they all have the same basic shape. So the bad news, again, is this. If I ask you to go from f double prime back to f prime, if I ever do an antiderivative, I have a family of functions. So I can't tell you which one exactly it is. And then if I go back again, I'm going to have another family of functions that I still can't tell you anything about because there's an infinite number of them. That is why I provided you this information. I am giving you 1 point on the derivative, and I'm giving you 1 point on the original function f. So what that allows you to do is when you're going backwards, if I give you 1 point on the, when you go backwards, if I give you 1 point on that graph, what it allows you to do is instead of looking at all these possibilities, if I give you a point on this graph, right? Like let's say I give you some point and I say that point has to live on the function, then now you know which function it is, don't you? That nails down the precise function. So we should be able to go backwards so long as we have this additional information. Let's see it play out and then I can answer questions. So you ready? Let's try this. So I'm going to start out again. Here's the second derivative. Second derivative of the function is 4x. Okay. Well, what is the first derivative of this then? Well, we're going to go backwards, right? So the first derivative, to get from here to here, I'm going to do an antiderivative. And we should all be comfortable with the idea that that's 4 times 1/2 x squared. So I brought the 4 for the ride. This was x to the first power. So I did the power rule. 1 over 1 plus 1, x to the 1 plus 1. Do I need to show that, or are you all comfortable with that? Everyone good? Sure, sure. So this is just 2x squared, right? Plus some constant, right? Plus some constant. I don't know the constant. I don't know what it is. But I know that f prime of 1 must equal, I have it here, 8, right? Which means when I plug 1 into this derivative, right? There's the derivative. When I plug 1 in for this, I need to get 8 to come out. So when I do 2 times 1 squared plus c, that must equal 8. And so now 1 squared is 1, so you just get 2 plus c is 8. And if you subtract 2 on both sides, you get 6 for c, right? So now you know what c is, which means that now you know exactly what the derivative is. It is 2x squared plus 6. We have f prime of x, right? Exactly. We know which one it is exactly. Questions? So we've gone back 1 step. Now we're going to go back again. Okay, we're going to go back again to get to f. Right now we're at f prime. Let's go backwards again. So we're going to take f prime of x is equal to 2x squared plus 6. And we're going to do the antiderivative. And that will take us to f. Now the 2 comes for the ride. This is x squared, so the antiderivative of that would be 1/3 x cubed plus the antiderivative of 6, which would just be 6x, and then plus c again, right? Plus a constant. Now, just because where we're headed with this, I'm not going to use c again. I'm going to use capital D, only because c is a constant, all right? We can call, I don't want us to confuse this c from here with a different c in the same problem. So I'm going to call it D instead of c. Is that all right with you? Just so we don't be, we're not going to get two different values for c within the same problem. All right, so I have that. I'm like, okay, well, I've got the function, but I don't know what D is, right? But I was given some information. I was given that f of 2 is 4. So now I know that when I plug 2 into this function, it better spit out 4, right? So let's, oh, and I should have cleaned this up. This up here, this was 2/3 x cubed. I just want to put the 2 and the 1/3 together, plus 6x plus capital D. All right, so when I plug 2 into that, oh, it's going to get ugly. 2/3 plug into 2 cubed plus 6 times 2 plus D. When I plug that 2 in, I should get 4, right? All right, this 2 cubed is 8, 8 times 2 is 16, so I have 16/3 here, plus 12, plus D must be 4. We're gonna get a fraction, unfortunately. Let's move everything to the other side, except D. D is 4, take away 12, take away 16/3. Now follow me, I'm just solving an equation here. This is -8 minus 16/3. And then I need a common denominator, so -24/3, right? 24/3 is -8. So minus 16/3. So D must be -40/3, -40/3. So remember, I didn't know exactly what f of x is. Now I do. F of x is 2/3 x cubed plus 6x minus 40/3. All right. Y'all with me on this? You with me? Questions? Let's do something kind of, I think this will be fun. I've never done this before in this class where I actually take the time to like really visually show you what we just did. So we had this thing, it was the second derivative. I'm going to call it h. I don't know. Yeah, I'll call it h of x here. I gave you this function, that was 4x, right? That was the second derivative. And then what we did is we found the antiderivative of that, we'll call it g. And whoa, what the heck? G of x. The antiderivative of that was what, 2x squared, right? Plus some c. So C, it could be any of these. See, I'm moving this up and down. It could have been any of these, right? Any of these. But I told you that the derivative, when you plug 1 into it, what do you get? When you plug 1 in, you get what?
6.
It was 6. So what I'm telling you is that, you know what? This blue curve that we're trying to find, it's gotta pass through that point. So that means I've got to move my C up. What was our C? What did our C turn out to be? 4?
I don't. Oh no, it was 1 ended at 4, and then the C
Oh,
was
no,
6.
yeah.
Yeah.
Sorry, it had at 1, it had to be 8, right? When we plugged
Yeah.
in 1.
Okay.
Okay, so when we plugged in 1, we needed to be at 8. So we needed to be up here. Do you see that? This C, we needed to figure out what C would give us the function that goes right through that point. So there's only one that goes through that point. you all see that? So that nails down that function exactly. So let me graph that. That's 2x squared plus 6. Okay, so there it is, right? There it is. We got that one. That's f prime. Now we got to go back to f. So when we went back to f, we took the antiderivative again, and we said that that turned out to be 2/3 x cubed plus 6x plus some c. Zoom out. Yeah, so let me do a different color here. Let's make it green. Okay, so the green one is the original f function, and it could be any of these. I'm moving c around right now. Okay, so it's changing the shape. But I told you that when you plug in, when you plug in 2 into the original function, you should get 4. So that means the point 2,4 had to be on that function, which is that one, that point right there. So I needed to somehow figure out, you know what, let me do D here so it matches what we did in the work. C had to be, yeah. So we were trying to figure out, how do we move this around? I actually need to move it more. Okay, so now I'm trying to move this around where I can make it go through that point. And what did we figure out D had to be? What was it? -40/3, something like that?
Yeah.
So if I type that in here, -40/3, there it is. It goes through that point. All right. So when there's a problem when you go backwards, antiderivatives, there's a problem that when you go backwards, you get this plus c, which gives you this constant, which you don't, that gives you the family of functions. You can't really tell me exactly which one it is. But if I just provide you one point on that function, then you can nail down which one it is. All right. I hope that visually makes some sense. All right, let's do another problem. You ready? I'm actually going to take the same problem and make a slight change to it. All right. So I'm going to take this problem, copy it, paste it. And now, same thing. I'm giving you the second derivative, right? Now look at what else I'm going to give you. F of, let's go ahead and push it. F of 1 equals -6. And f of 2 equals 4. So what's different here? I gave you the second derivative, right? And I'm asking you to find the original function f of x. I'm asking you to find that. So you got to go backwards twice, right? But what about the other information I gave you? What's different?
We don't have any information on the first derivative.
That's right. I didn't give you any information about the first derivative. What I gave you was information about the original function, but I gave you 2 pieces of information, right? So instead of me giving you 1 point on the derivative and 1 point on the original function and asking you to go backwards, I'm not giving you any information about the first derivative, and I'm giving you 2 pieces of information about the original function. So let's work through it and see how we're going to get around this. So we're going to take this, we're going to do the antiderivative. We've already done this. The antiderivative of that was 2x squared plus c, right? And we don't know what c is. And unfortunately, we don't have any information about the derivative, so I'm not going to be able to tell you what c is, right? I can't. But I can still do the antiderivative again. Watch. The original function, because I'm doing the antiderivative of the derivative, should be the 2/3 x cubed, right? 2/3 x cubed, plus now the antiderivative of c. What's the antiderivative of c? C is a constant. We don't know what it is, right? So what's its antiderivative?
Cx.
Cx, right? Just like if it was 6, the antiderivative would be 6x, right? but it's C and we don't know what C is. So we're just going to say CX. Y'all understand? But we're taking an antiderivative. So we have to add to it a constant that we don't know, D, which is a different constant. So this is what I know about F so far. I know F of X must be 2/3 X cubed plus some constant times X plus some other constant. And I don't know what either one of those are, right? But I have some information. I know that when I plug 1 into the original function, I should get -6. You know what? Yeah, we're just going to have fractions. I could make the problem easier, but let's just do it with fractions. So when I plug 1 into this function, it better spit out 6. So let's replace all the x's with 1s. 2/3 times 1 cubed plus c times 1 plus d, that must be -6. All right, that's just 2/3 plus c plus d must equal -6, which means c plus d must equal -6 minus 2/3. I decided to move the 2/3 to the other side, which means that c plus d must be -18/3 minus 2/3, getting a common denominator, which means that c plus d must equal -20/3. Now, did I solve for C and D? No. But what I have is an equation that has C and D in it, right? I don't know the solution to that. There's an infinite number of C's and D's that would make that true right now. I could pick, like if C is 0, D would be -20/3. Or I could say C is -20/3 and D is 0. There's an infinite number of answers. So how am I going to figure out what C and D are? Well, I've only used one of the two pieces of information I have, right? The other piece of information I have is that when you plug in 2, you should get 4. So let's try that. When you plug in 2 into this function, you should get 4. So let's replace all the x's with 2's. And that should spit out a 4. So 2 cubed is 8, 8 times 2, this is 16/3, plus 2c plus d equals 4. Do y'all see where I'm going with this? What am I about to create here? What do we call this in college algebra when you have 2 equations and then 2 things you don't know? System of equations. System of equations. That's what I'm about to create, is a system of equations. So let's go. 2c plus d equals 4. Take away 16/3 because I'm just subtracting that on that side. 2c plus d equals common denominator. So 12/3 minus 16/3. So 2c plus d must equal -4/3. That is my second equation. 2 equations, 2 unknown variables. I have a system of equations. So let me go and give you the algebra notation for this. When we're doing systems of equations in college algebra, you would do something like this. Right, remember that you'd put this brace in front and that would tell you, hey, we're trying to solve the system of equations. Normally in college algebra, we use like X and Y in the system, but they're just 2 unknown variables. So it's exactly the same thing, right? All right, how do we solve that?
Elimination.
You have 2 choices, don't you? You have substitution and elimination. Those are your 2 options when it comes to solving systems of equations. I don't care which one you use. This is college algebra. How do I know this is college algebra? Because my college algebra class, just the other day, we were solving systems of equations, okay? That's why I know this is a college algebra topic. Actually, we were doing, this is a system of 2 equations, right? There are two methods, substitution and elimination are the two methods. You should be comfortable with both of them. Now, I understand it's been a long time, right? Pre-cal and, go back 2 semesters, right? But you've seen it before. So I'm going to do elimination now. Here we go. So the way elimination works, the way that I think about elimination is I look at the variables C and I think to myself, what could I do to make those two cancel out and become a 0 if I added them together? So I would have to make this top one a -2C, right? Then if I add them down together, they would become a 0. So I have to make that a -2C. So to do that, I multiply the top row by -2. Now, you could have done the same thing with the D's and tried to make the D's cancel. I'm doing the C's. This is elimination, what I'm doing, and you have the freedom to choose which variable you want to attack. I'm attacking the C. So I'm going to distribute 2 through to everything, okay? And that will create a new system of equations. It becomes -2C, distribute that -2 through, -2D, and then on the other side, it will now become +40/3 because you're multiplying -20 by -2. So it doubles it, but makes it positive. Your bottom equation stays. For those of you who like substitution, substitution is different, right? You solve one of these equations for C or D and then plug it into the other equation. You're free to do that as well. I like this method though. So now what we do is we add down, okay? We add. And so these cancel. Here we get -D, and then we have to add these down. And fortunately for us, these already have the same denominator. So this is 40/3, take away 4/3. That's 36/3. Is that right? Does that actually turn out to be a nice number? 12, right? -D is 12. Multiply both sides by -1. D is -12. Wow. Okay, we know what D is. Okay. Once we know what D is, we go get C. And you can get C by plugging this D into any equation you see here. Any of them, doesn't matter. So I'm just going to pick one. I'm going to pick this one right here. I'm going to take that one. C plus D is -20/3. But I know that D is -12. So C minus 12 is -20/3. And that means C is 12 minus 20/3, adding 12 to both sides, which means C is, I need a common denominator, 36/3 minus 20/3, which means C is 16/3. There we go. That's what C is. It's a little harder. This one's a little harder than the previous one, yes? You have to solve a system of equations at the end. That's harder. But I now know what F is, don't I? I know the exact function we're talking about. So let me go back up. Where was the function? Right here. This was our function, but we didn't know what C was. We didn't know what D was. Now we do. So my function that we're talking about is the function 2/3 x cubed plus what was C? C was 16/3. So plus 16/3 x, right? And then plus D, but D was -12. There it is. That's f of x. All right. That was fun, huh? I'm not going to go through a visual of this one, all right, because of time. All right, next thing I want you to know, recall when we first started talking about first and second derivatives, if f of t is the position of an object, then f prime of t Do y'all remember if the function gives you the position of an object, what does the first derivative give you? Do you remember?
Velocity.
Velocity is the velocity of object. And the second derivative gives you what?
Acceleration. Of object.
Acceleration. Yeah, acceleration. Acceleration. So visually, it looks like this. If I give you some function f of t, right, which gives you, like graphically, this is time and this is distance, okay? Then when we take the derivative of it, you now have a new graph where this is time and this is velocity, whatever that's going to look like. And then if you take the derivative again, you get a new function where this is time and wait, distance, time, and this is acceleration. Okay. And that's going to be a graph. So please, please, please don't leave Cal 1 without knowing that. If you start with a position function, the first derivative is the velocity function, the second derivative is the acceleration function. You'll get to a physics class and you'll be talking about a spring that's moving. And they'll say, oh, the spring looks like a sine function. And they say, okay, the spring is moving, here's the sine function, what's its velocity? And you're like, well, I don't know what the velocity is, I only know where it is. Well, you do know the velocity, you need to take the derivative of that function. Then you know its velocity, all right? So please make sure you understand that connection from position to velocity to acceleration. So, okay, understand? So the idea of antiderivative would be if we started with acceleration, we should be able to go backwards to velocity. And if we go backwards from velocity, we should be able to do the antiderivative and get position, right? Position. But we know it's not that easy to go backwards, right? We know it's not that easy because when you go backwards, you have a family of functions. So we have to nail it down somehow, which means you have to give me some more information. And then to go back from velocity to position, you would have to give me some more information. So I'm showing you this for a reason. Have you all ever seen this function, either in a physics class or in college algebra? Does it look familiar? Has anyone ever seen that before?
Physics, I think.
The what?
Is that I think I've seen it in physics where like the V0 is like the initial.
The initial velocity. Mhm.
The initial velocity and initial distance. Yeah.
That's right. So this is your initial meaning like starting velocity. And this means initial or starting position or distance. So the formula I gave you right here, this is the formula that we use on planet Earth. If you drop an object from any height, if you tell me the initial position, so maybe you dropped it from a 40-story building. Okay, so you give me the height, maybe it's like 700 feet. You drop something, you replace that with 700 because that's where you drop it from. And then the initial velocity is whether or not you just dropped it, or if you threw it down, or if you threw it up before you let it go, right? That would be your initial velocity. This formula will tell you exactly how high off the ground that object will be after a certain amount of time. Okay, that's the formula. Now, it takes out air. You have to take out air resistance for this formula to work. If you want air resistance, the formula becomes more complicated. But in physics, we start with baby steps, right? It's always baby steps in physics. You start looking at things, you're like, act like there's no friction, you know, and then later on you put friction into things. And so here is the formula for all objects falling on Earth. Okay, it'll tell you exactly where it is at any point in time. Got it? Understand? I mean, like, if you've seen it, you've seen it. I'm going to show you where it comes from now. All right. because we can actually generate this formula. So when you drop an object, right, when you take a rock, let's say, and you drop it, the only force acting on that rock as soon as you let it go is gravity. And gravity is pretty much constant. I mean, it depends on where you are, and it's inversely proportional. We're not going to get into like real technicalities. You know, if we're somewhere reasonable near the let's say sea level or so, gravity is pretty constant throughout, right? Does anybody know what the well, gravity is an acceleration. We should say that it's a force and it's an acceleration. Does anyone know the acceleration of gravity? What the acceleration of gravity is?
9.8.
It's 9.8 meters per second per second. And actually it's negative because it's directed towards the center of the earth, and positive acceleration is measured upward. Okay, that is the acceleration of gravity. That has been measured, that has been accurately measured, okay? Well, I'm going to convert this to feet per second. It's approximately -32 feet per second per second. All right, so we can measure things in meters or in feet or in miles. I'm going to put it in feet per second because this formula here is in feet, measures things in feet and seconds. All right. So here's the amazing thing. This is the acceleration function on Earth for objects falling. So I'm telling you right now that this function over here is this. It's a constant, right? It's a constant. So let's act like that. We have some acceleration function. I'll call it a of t. It is -32. Can you then tell me what the velocity function is? Sure, just go backwards, right? Do the antiderivative. What's the antiderivative of this?
-32t.
Plus
T.
Plus some c, right? Plus some c. I don't know what c is. Now, from here, can you go back and get me the position, which would, I'll call it d of t. Can you give me the position? Well, it would be -32 times the antiderivative of t, which is 1/2 t squared, plus the antiderivative of c, which would be c times t, plus some constant, I don't know, d, right? This is -16 t squared plus c times t plus d. Does that look familiar? Is that not just this formula up here, but v naught is c and d naught is d? All right, well, why is c equal to the initial velocity? When we say initial velocity, what we're saying is when t is 0, right? When t is 0. So if I told you right now to go into this velocity function and plug in 0, right? Wouldn't you get just c? So isn't c the initial velocity? Isn't it the velocity at time equals 0? So let's just not call it c, let's call it v naught. That way we all understand that it's the starting velocity. And then you can do the same thing for d. To figure out what d is, that's the starting position. So at t equals 0, into this right here, you get d would be your starting position. So we replace it with d naught.
I have a question.
Yes.
If t is equal to 0, wouldn't that term c times t also equal 0?
That's right. It would. All of this would go away, and so you get d, wouldn't it?
Yeah.
So d would be the position of where you are at time 0.
Right.
Right? Which is that last number, which is what the d naught means. D naught is your initial position.
Yeah, that makes sense. I'm just understanding how C times T doesn't also just go away when we say, like, why is it V naught? Why is it just not 0?
Oh, well, maybe, okay, maybe I should have explained it a different way. Okay, let's just ignore all this, right? Ignore all this. Remember, we started with acceleration, we went backwards, right? We went to the velocity, but we didn't know what C was. But do you know what happens to the velocity function when I plug in 0? What do I get when I plug 0 into this?
Just C.
C. But do you agree that that should be my starting velocity then?
Oh, yes, that hence V
Right.
naught.
Right? So C should be V naught, should be the velocity at the initial part. So now I know what C really means, right?
Yeah.
Okay, then when we did the antiderivative, right? We now know that this C is V naught. But
Mhm.
now I say, okay, what's your position at 0? At the very beginning of time, where are you? Well, it kills everything except D, right?
Yeah.
So D is going to be your starting position. So let's call it D naught. Does that make more sense?
Yes,
I
absolutely.
should have explained it that way. I normally explain it that way. I don't know why I didn't this time, but okay, so that's, I just wanted to show you that formula from physics. It actually just comes from taking the antiderivative twice. What I think is amazing about this is this means that an object falling on Earth, there's a quadratic function that dictates where it's going to be at every point in time, right? It's a quadratic function, but it's the same on any other planet with gravity. It's same in the sense that it's a quadratic. Regardless of what planet you're on, as long as your acceleration of gravity is constant, I promise you that the position function for an object falling on that planet will be a quadratic. How do I know that? Because if your acceleration is constant and you do the antiderivative twice, you're going to wind up with a t squared. It's never going to be t cubed. It's never going to be t. It's always going to be t squared. So you're always going to be quadratic. Does that make sense? So you can model this, you can model objects falling on different planets so long as you can somehow have a measurement of their acceleration of gravity. It's kind of interesting. It's just the way the universe works, all right? All right, I'm ready to move on. You should now be able to handle the rest of the problems from 4.7. There were some problems I told you to not look at, right? I told you not to do 14 through 29, those right there, right? So now you can, because those are problems where they give you the second derivative and ask you to go backwards to the original function. And they give you some conditions like I did today just now. And I believe there's only one that has a system of equations. Yeah, only number 33. Oh, 33 is not on here. I would do number 33 if I were you. All right, I'm ready to move on. Y'all ready to move on? Okay, trying to think about the order in which I want to do this. Yeah. All right, so we've gotten to this habit now where I keep asking you to find the antiderivative of something, right? I keep on giving you a function saying, hey, go find the antiderivative. Go find the antiderivative, right? Go find the antiderivative. There needs to be a better way for me to actually ask you to do that. I need some notation. It's kind of like, you know, what we've studied before is if I gave you a function like this, and if I wanted you to go take the derivative, right? All I would do is say find f prime of x, right? And you would know what you need to do now. I need some notation to tell you to find the antiderivative without me like writing it down or typing it down. Go find the antiderivative. So you ready for some notation? All right. So notation for finding antiderivatives. All right, so let's say that I want you to do this. So let's say f of x is 4x, and I want capital F of x, the antiderivative, right? Let's say I'm trying to get you to take 4x and give me its antiderivative. This is what I will write. I will write this. That's what I'm going to write. Okay, now I'm going to tell you what all this means, but that's the notation. So this is telling you to look at this right here, 4x, and tell me its antiderivative. So your answer to this would be 2x squared plus c. Okay, right? That's the antiderivative of 4x. Well, let me get to where it shows you what all this notation means, what it's called, the language of it. Okay, so let me make this a little bigger for you. So if we're given a function f of x, right, we're given some function. If we wish to find the general antiderivative, then we will write this symbol, the function, a dx. That's the notation. And then, of course, the answer is the capital F. It's the antiderivative plus some constant. This whole thing together, this whole thing right here, is called the indefinite integral. The indefinite integral. That's what it's called, okay? You could call it the antiderivative if you want, but it's also called the indefinite integral. That symbol in the front, think of it like the letter S that's been stretched out vertically, okay? It actually comes from an idea that I'm not going to be able to get into in this class, where this has to do with summations, and in Cal 2, I will get into it. If you're in my class, I will talk about it, okay? But for now, I just want you to know it's an S that's been stretched out, all right? That is called the integral sign. The integral sign. The function that you're trying to find the antiderivative of is called the integrand. The integrand is the function itself, all right, that you're trying to find the antiderivative of. Now, this dx is probably the most confusing thing out of all the notation. It has to be there, okay? And it's hard right now to explain what it means and why it's there. Right now, this dx, we're going to call it the differential, and we will explore that a little bit more in a minute, okay? Just realize, look at it as a way of keeping track of what your variable is. So like the variable in the problem is x. dx keeps track of that. And you may be like, well, I don't need it to keep track of that because the function itself, right? Like 4x, you see that 4x right there, already told me what the variable was. So why do I need dx? Well, you don't always have functions that only have one variable. Like you could have two variables in there, like x and y, and you could have three variables like x, y, and z. And we could do substitutions where we replace variables with other variables, and it can get really complicated. So it's a way of keeping track of the variable, all right? That's a very kind of loose way of explaining what it is, but it needs to be in the notation. All right. The capital F that you find, okay, the capital F that you actually find, this thing right there, that is called the antiderivative of that little function f. And I have to scroll down here, unfortunately. So let me scroll down. The C that you put on the end, that if you forget, some professors count it completely wrong. That is called the constant of integration. So a lot of new language here, right? This thing called the indefinite integral, the integral sign, the integrand, the differential, the antiderivative, the constant of integration, right? These are all new terminologies for us. The process of finding antiderivatives of functions is called integration. That's what it's called. So when we were in Cal 1, we were taking functions and finding derivatives, right? That was called differentiation. Cal 2, we're taking functions, finding antiderivatives. That is called integration. That is why Cal 1 is called differential calculus and Cal 2 is called integral calculus. Cal 1, differentiation, Cal 2, integration. So we're going to be doing everything that we did in Cal 1 backwards now in Cal 2. So that what I just said is really important. We're going to be doing in Cal 2, you're going to be doing everything you did in Cal 1 backwards. So if you don't know how to go forward very well, going backwards is going to be nearly impossible for you. And I'm just saying that to you because, like, if you struggle with product rule, chain rule, any of those, if those things, they will haunt you in Cal 2. They will haunt you to the point where you have to take Cal 2 3 times because you never understood Cal 1 well enough. So my suggestion is always that make sure you come out of Cal 1 feeling real good about all your product rule, quotient rule, chain rule, all that stuff, because it's like now you need to run a marathon, right? If you don't know how to put your shoes on, you ain't running a marathon, all right? I don't know if I'm terrible with analogies, but it's just, I can't understate how important your understanding of the Cal 1 stuff is. The better you are at it, the easier Cal 2 will be, and it's still going to be hard. Even for the best students in here, Cal 2 is going to be hard. All right. So, all right. So what have we learned? Yes.
Sorry. You said that the indefinite integral is the antiderivative, but then capital F of X is also the antiderivative. So can you say capital F of X is the indefinite integral?
Well, this notation by itself, standing alone, would be called the indefinite integral.
Okay.
But your answer, it is equivalent, right? It is equal to the antiderivative of the little function, right?
Mm-hmm.
So you wouldn't want to call this capital F of X the indefinite integral. You would want to call that the antiderivative. The left side you would call the indefinite integral, but they are equivalent, right? They are equal to one another.
Gotcha.
Yeah.
That makes sense.
Good question. I understand what the confusion there, because it's almost like there's two names for the same thing, but it's really one name for each side, but they are equivalent, right?
Yeah. And one more thing about the dx, you're saying that's to keep our variables straight. So if there was like a y in there, would it be dy?
Well, no, you could still be doing an antiderivative where x is the thing that you're treating as the independent variable. So do you remember that story I told you about the girl that I met? And I was like, hey, what's the derivative of x? And she said, with respect to what variable?
Yeah.
Okay. It's the same idea with the antiderivative. It's like, what's the antiderivative of x? Well, with respect to what variable? If it's with respect to x, the antiderivative would be 1/2 x squared plus c.
Right.
But if it's with respect to some other variable like y, then the answer is going to be different. And this really only becomes super, super important in Cal 3, because in Cal 3, that's called multivariable calculus, where your variables now are x, y, z, whatever, however many you want. And so you constantly have to know what variable is independent and which ones are dependent. So you have to have a way of keeping track of it.
Okay, so similar to how when we would do dy over dt with respect to, we were differentiating with respect to t. So it's still, and then you do chain rule and okay.
It is the chain. It's basically the dx is the chain rule. It's the popping out, like if I said, take the derivative of x squared with respect to x, you would just say 2x, right?
Yeah.
But next to that is also a dx, right?
Yeah.
Because you're taking derivative of x with respect to itself. And that always became a 1, right? So this kind of dx over dx is kind of like where this piece is coming from. It's not exactly, but it's close enough. There's a very, very nice way I can explain what dx is. That's geometric, but it requires like an entire day of me developing that. So I can't get too much into it, but there is a very nice, very, very nice way of understanding what dx really is. So I would just stay tuned. It'll become more clear as you start to get through the forest here.
Thank you.
Right now, just think about the notation and like, okay, understanding what the notation is. Okay, so look, what have we seen already? This notation now makes sense. Okay, find the indefinite integral, right, of x to the n, treating x like your variable. So that's just x to the n. Well, we already established that formula, didn't we, last class? It's 1 over n plus 1, x to the n plus 1 plus a constant, so long as n's not equal to -1, and it's natural log of the absolute value of x. Notice the absolute value. From here on out, when you do the antiderivative of 1 over x, put absolute value around your answer. So natural log of absolute value of x. That just fixes some domain issues that we have. All right. We good? You hanging in there? Let's just practice the notation. Not like this is going to be a hard problem or anything. Let's just practice the notation. So what if I said find this? I'm asking you to find me the antiderivative of that, right? That's all I'm asking you to do. Find me the antiderivative. So you would just look at these separately because there's addition and subtraction between them. You can do them one at a time. 1/3 x cubed minus 1/2 x squared. What is the antiderivative of cosine x? Not the derivative, the antiderivative.
Sin x.
Sine x, just sine x, right? Not negative sine x, because you're doing an antiderivative, not a derivative. And then plus c. We're done. That's just notation, right? You understand? Okay. You should be able to handle x raised to any power. And you should also be able to handle things that you recognize from Cal 1. I'll give you one more. What about this? So you're thinking about Cal 1, you're going, okay, do I remember in Cal 1 ever taking the derivative of something and getting secant squared x?
Tangent.
Tangent. So the antiderivative of this is tangent x plus c. We're done. Now, if you don't remember that, it's going to make it harder for you, right? Like if you don't remember the common stuff from Cal 1, it's going to be difficult in Cal 2 because you're like, oh, I don't remember that. So always make sure that make sure that you've, before you start Cal 2, that you refresh yourself on these common derivatives that we came across a lot, like tangent, sine, cosine, tangent, right? Make sure you're familiar with those. All right, I'm ready to throw you into the fire. Are you ready to go into the fire? Oh, yes, you are. You're ready. You're ready. You don't realize you're ready. All right. Let's see how bad this gets, how fast this gets bad, okay? If we're trying to find antiderivatives. So let me start it with this. If I asked you right now to look at this function, and I asked you to take its derivative, could you do that? I hope so. I hope you would be like 1 times sine x squared plus cosine of x squared times 2x times x. I hope that it would be almost that fast for you at this point. You're running a product rule, right? A product rule on this. And you have a little bit of chain rule involved here as well. All right? This is Cal 1. It's very systematic, right? I just use product rule. Cal 2. What's the antiderivative of that? Not so easy. Not so easy. It's complicated, right? It's very complicated because we need to figure out what you take the derivative of to get this as an answer, right? To get this as an answer. If you ask me to take derivative, I have no problem. I have a rule, a product rule. I'm like a machine. Derivative of the first one times the second plus derivative of the second times the first, right? I mean, it's very mechanical. Backwards, the mechanics are gone. There's intuition. There's a lot of other things that are hard to teach. That's why I say it's so good. It's so much better for you to be good in the Cal 1, because the intuition comes from your comfort level with Cal 1. That's where the intuition to go backwards is. All right. You ready to see this? Right now, the only thing we can handle is if we have x to a power, right? We can do that. We can do the integral of that, right? We can handle that. If we have an integral where we have something plus something minus something plus, doesn't matter. We can handle that because we can handle as long as we can break it up, right? We can break it up. We know how to do that. But now what we have are two things being multiplied, right? And we're trying to find the antiderivative. And this is where we go. I don't know how to make this expressive, like yelling. I don't know. This is where you're like, what do you do to undo the product? How do you undo a product rule? There is no rule. Unfortunately, in Cal 2, I'm never going to be able to hand you a rule to say, this is what you do every time you have a product. It doesn't exist, okay? There is no rule. So what we have are strategies, all right? So I'm looking at this and I'm realizing, you know what? It's not this, okay? It's not x to a power by itself. It's not a bunch of things being added and subtracted. But it is a product, and I know that that means life's going to be kind of messy now. So the first sort of technique that you learn in Cal 2, the first thing that we learn is something called substitution. And this is the easiest out of all the methods, all the different, you're going to learn, in Cal 2, you're going to learn a couple of different techniques. The first technique is called substitution. The second technique is called integration by parts. The third technique is called trig integrals, then trigonometric substitution, and then something called partial fraction decomposition. Those are the 5 strategies for doing antiderivatives. The first is substitution, and it's the easiest when compared to the others. When you learn it, though, the first time, you're like, well, this ain't so easy. But relatively speaking, it's the easiest of all right? So here's the way substitution works. And it's really, there's not like a, I wish there was a set of steps, everyone. There's not really a set of steps. What I'm going to do is this. I actually have the steps written down here. Hold on. Here it is. I'm gonna start a new page. So this is the kind of strategy that we're going to use. We've got 20 minutes. Let's see if we can knock this problem out in 20 minutes. It shouldn't take us that long. We're going to look at this integral x sine of x squared dx. What I'm going to do, because I realize it's nothing easy, right? I'm going to look at the integrand. Okay, everyone take a look at the integrand. Here's the integrand. There it is right there. Okay, I'm going to take a look at that. And what I'm going to do is I'm going to try to find something. All right, now I'm not even going to tell you what that something is because I don't even know what it is myself right now. It's just something. I'm looking for something. And I also want to see its derivative, meaning whatever the something is that you're seeing, you need to also see its derivative. Do y'all see it? Do y'all see something in its derivative? What is it? What is the something that you're seeing, and then what is its derivative? I saw people shaking their head yes, so that's why I'm asking. Do y'all see x squared?
Yes.
If I said that was the something that I'm seeing, do you see its derivative anywhere? What's the derivative of x squared?
2x.
2x. I don't see 2x. What I see is x, right? That is the derivative of the something. Not quite though, right? I'm off. I'm off a little bit. I'm off by 2, aren't I? It'd be real nice if I had a 2 there. Well, look at what step 3 says here. The derivative, the derivative that you're looking at, the x that we're seeing there should appear in the numerator, not be trapped. Okay, so is this x in the numerator? Well, I don't really even have a fraction, do I? So it is in the numerator. It's not trapped, meaning that it's not like stuck under a square root or inside of a parentheses. It's all out here by itself, right? So far I've looked for something, x squared. I've seen its derivative, kind of, x. It's 2x actually, but I have an x. That x is in the numerator. The derivative might be off by a constant. Oh, okay, good. It is off by a constant, right? Like the derivative is 2x, I have x, I'm off by 2. That's okay. It's okay to be off, all right? It's okay to be off. If those things happen, then you're gonna make a substitution. Okay, so let me just back up. I'm looking for something, x squared. I need to see its derivative somewhere, 2x. I'm looking for 2x. I see an x. I'm off by 2, it's okay. It's okay to be off by a constant. And that x that I see is in the numerator. It's not trapped, it's not in the denominator, it's free, okay? So if that happens, then you're going to let u be equal to the something that you found, all right? So here we go. Now let me do it. Let me do it. Just hang tight. I'm going to now let u be equal to x squared, okay? So wherever I see a x squared, I'm going to replace it with u. Got it? All right, I'm going to replace it with u. But I want to do something here. I want you to take the derivative on both sides of that equation with respect to x. So take this equation right here where we made the substitution. Take the derivative with respect to x on the left and take the derivative with respect to x on the right, and you get 2x. Y'all still with me? Now I want you to do this. I want you to multiply both sides by dx. Y'all still there? I saw something, I replaced it with u, I took the derivative of u with respect to x, and then I multiply both sides by dx. Now watch what I do now. This is where the magic happens. I'm going to rewrite this integral, and I'm going to rearrange things. Because that x in front was not trapped, I'm going to slide it to the back next to the dx. Right? And now I'm going to play a matching game. I'm going to look and see over here in this equation, I have x dx right there. Do you see that x dx right there? Well, I can solve this equation for x dx if I divide both sides by 2 or multiply by a half. So I'm going to do half of du equals x dx. Do you see how I made that turn into that x dx now looks exactly like this? Which means that I can replace everything in green with half of du. Everything in green will be replaced with half of du. And everything that's blue will be replaced with u. Because isn't x squared what we said u was? If I do that, what will my new integral look like? Antiderivative sine of what? What's x squared?
U.
U.
And what is x dx turning into?
Half du.
Half of du. Okay. We're getting somewhere, believe it or not. Watch my next step. I'm gonna bring the 1/2 out in front and now just sit here and look at sine u du. Now, the reason I brought the 1/2 out in front is because 1/2 is attached to this function. And so when I find the antiderivative, the 1/2 is going to come for the ride. So I'm just going to choose to bring the 1/2 out completely out of this and just focus all my attention now on figuring out what the antiderivative of sine of u is. So what is the antiderivative of sine of u?
Negative cosine.
Negative cosine of
U.
u, right? Negative cosine of u. Which means this should turn into 1/2 times negative cosine of u plus c, which is negative 1/2 cosine of u plus c. But what was u?
X squared.
X squared. So negative 1/2 cosine of x squared plus c. There it is. That's the antiderivative. I'll go through this again, okay? But let's just check to see that that's correct. Is this the correct answer? How could you check? Take the derivative, right? Take the derivative of this. So if I asked you to take the derivative of this, negative 1/2 would come for the ride. What's the derivative of cosine of something?
Negative cosine, negative sine of something.
Negative sine of that something. Chain rule times derivative what's inside?
2x.
2x. What happens here? 2's cancel. Negative and negative become positive. And so all you're left with is sine of x squared times x, which if you move the x to the front, you will get that. Welcome to Cal 2. Let's go back and just rethink it. We're going to have time for one more problem. Okay, I sat here, I said, you know what, this is nothing easy. So I'm looking for something in its derivative. Ah, x squared, I know the derivative, that's 2x. I have x, I don't have 2x, that's okay. I'm going to make sure that that x is not trapped. It's not in a parenthesis, it's not in a denominator, it's not underneath the square root. It's nice, it's just sitting there. So I replace, I call x squared u. I differentiate with respect to x on both sides. I multiply both sides by dx, and then I play this matching game where I move the x to the outside and I try and replace this x dx with something. And I had to basically scale both sides by 1/2 to do this. Once I saw what I could do to replace the x squared and the x dx, I replaced them with u's, stuff with u's in it. And then just here, it was just a clean antiderivative. Well, I hope that's a clean antiderivative. The antiderivative of sine of u is negative cosine of u. And then just plug everything back in. Let's do another one. Yeah, I think we should do another one for sure. Some of the looks on your faces. I'm just going to go to the book and see what they have here for us. Oh, yeah. Yeah. Okay, we'll do that. We'll do something like this one. So how about this? I'm going to let you sit here and think about this while I go refill my very strong drink. Look in there, see if you can figure out what u should be. Try and figure out if you see something and its derivative is there. It's okay. It's off, if it's off by a constant. Take a minute. And then why don't you just let me know on the poll if you think you know what the u should be here. And actually, if you think you know, you should maybe in the chat, tell me what you think it should be. Because I think you could type in what the u is in the chat. If you want to, you don't have to. I just be curious to see what people do. Like I was saying, what kind of makes things easier in your life is if you can visually just look at something and know what its derivative looks like, right? Because that's what you're needing to do here. I'm getting some interesting things. We'll go another minute. All right, time's up. I have some interesting things here. All right, so let's talk about some things it's not, okay? So I had this as a possibility. U is equal to just x cubed. Okay, well, if you said u is x cubed, the derivative of that with respect to x would be 3x squared. So I see u cubed, here it is, there's u cubed, great. But where is there an x squared? I don't see an x squared. I see an x to the fourth, but that's, I mean, I guess you could write that as an x squared squared, but isn't that in the denominator and isn't it like trapped under a square root? You don't want the derivative part to be in the denominator. You want it to be in the numerator and you want it to be untrapped, okay? So do y'all see this is no good, right? If I put a 5 in front of this, it doesn't change anything because then it would be 15x squared and that still the x squared's trapped or not in the numerator. I saw another one that said u is equal to x to the fourth. What do y'all think about this one? What's the derivative of that? 4x cubed, right? Do you see a 4x cubed? I see a 5x cubed, but that's okay. It's okay to be off by a constant, isn't it? Didn't I say it's okay to be off by a constant? So we would have a 4x cubed, but in the problem, it's a 5x cubed. That's good. This looks promising. And the x cubed that I have up here is not trapped. It's in the numerator. And if I wanted to, I could slide it to the side, which I'm going to do, right? Questions? Questions that this looks good? This looks promising? Any questions? Sorry. It's good, but it's not the best. The best choice for you is actually the 9 plus the x to the 4th. Grab the 9 as well. Why? Does that change the derivative? No, right? The derivative of this is still 4x cubed. Do you see? Now that may be like, oh, well, big deal. It's just the not, but it makes a huge difference when you make the substitution. So even though this looked pretty good, this is the best way to go. So I'm going to go with this. Next step is I'm going to multiply both sides by the dx. And now I'm going to start playing my game. You ready? I'm going to start playing my matching game. I'm going to try and rewrite this integral. Watch the way I rewrite it first. Let me know if you have any questions on what I'm doing. Yeah. That's fair, right? That's a legal algebraic move. I can just pop that 5x cubed off the side like that. Let me look at what matches. 9 plus x to the 4th, that is this. That's going to be replaced with u, right? Everything under that root's going to get replaced with u. Then I have this, see this x cubed dx? I've got an x cubed dx right here, don't I? Now I don't have a 5, and this 4 is a problem. So let me take care of those. I'm going on this equation. I'm going to multiply both sides by 1/4. That will get rid of the 4. And then I'm going to just pop this 5 out because it's a constant, so it should come to the right. So I have a 5 integral. Ready? I'm going to rewrite it. 1 over. I'm replacing the blue with what? U, right? Everything in blue is U. And then everything in yellow here gets replaced with 1/4 du. I'm running out of time. I'm going to pull the 1/4 out, so it becomes 5/4 on the outside because that can just pop out. And then this is really u to the -1/2 du. Why am I writing it as u to the -1/2? Power rule, right? Now I can use the power rule. This is like x to the -1/2, but it's a u instead of an x. So now antiderivative, right? 5/4. All right, the antiderivative should be 1 over -1/2 plus 1 u to the -1/2 plus 1 plus some constant. This is 5/4 times, let's see, 1 over 1/2 u to the 1/2 plus c. And then I can pop that up as a 2 and it'll reduce out. You should get 5/2. 5/2 u to the 1/2 is the same as the square root of u plus c. And this is 5/2 square root of u, but u was 9 plus x to the 4th plus c. There it is. That's your antiderivative. You could check this, couldn't you? I know we're out of time, but let's check it. Let's take derivative of that real quick. 5/2 comes for the ride. What is the derivative of the square root of something? 1 over 2 square roots of that something times the derivative of what was in the root which is 4x cubed. Things should go away here. Gone, gone, gone. Yeah, 5x cubed on top, square root of 9 plus x to the 4th on the bottom. That's it. Okay, we're out of time. So for what I'd like for you to do is look at section 5.5 in the book and look at problems 1 through 6. In these problems, they give you an integral, okay? And they tell you what the substitution should be. So they're not even making you have to do the process of figuring out what u should be. All right, they're giving it to you. So practice those if it's, but when they give you the u, I want you to look at the problem and understand why they're choosing that u. See if you can make your mind understand why that u is the correct u. All right. All right, next time we'll do more substitution. I'll just show you briefly the evaluation theorem and then we'll talk about the final. We good? Okay, y'all have a good one. And then do your 4.7 homework. Don't forget that. Have a great day.
Thank you. Bye.